Welcome to our paper, Dissecting Deep Metric Learning Losses for the Image Text Retrieval. I'm Xuan from Microsoft. Visual-Semantic Embedding is a prevalent approach in image text retrieval by learning a joint embedding space between the image and the language modalities where semantic similarity will be preserved. The triplet loss with high negative mining is a common objective for most of the VSE method. Inspired by recent progress in deep metric learning in the image domain, which give rise to the new loss functions that outperform the vanilla triplet loss. In this paper, we revisit these loss functions in the VSE tasks and propose a gradient framework which enable us to continue find a better objective for the VSE task. Here is an illustration of our gradient-based objective analysis framework. Most of demo losses design are under the common training pipeline. First, we need to design how to organize the embedding space. For example, in triplet loss, we require positive to be closer to the anchor than the negative. And then, we need to find the loss function which will penalize the cases where embedding points do not meet the design requirements. Then the autograde from PyTorch or TensorFlow will generate a gradient to guide the network moving the embedding space into the desired structure. In this process, we find the loss function is implicitly optimized the embedding space. Instead, it's the gradient directly optimizes the embedding space. Therefore, we propose the Go framework, which aims to design the gradient directly in optimizing the VSE model without the loss functions.
Before we introduce the gradient design, let's first do the general gradient analysis. In common, we input a pair of image and text into the image and text encoder to get the loss, and then these two encoders were updated with the gradient. And here we can see the gradient contain two items, and the first term is the gradient from loss to the feature. The second term is the gradient from the feature to the model parameters. We will mostly talk about the first term. And here is the expansion of the first term, and we can see in this expansion there contain two components. The first component is mostly varied by the different loss functions, and the second component is the corresponding positive and negative, and it should be same crossing different loss functions. For the scalar terms, we find that they can be divided by two sets. One is the triplet weights, and this weight are related both to the anchor positive similarity and anchor negative similarity. Here is three triplet weights we find from vanilla triplet loss, unshaded loss, and circle loss. And here is the triplet weight map. The x-axis represents the anchor positive similarity, and the y-axis represents the anchor negative similarity. And another set is the pair weight. This weight are related either to the anchor positive similarity or anchor negative similarity. Here is 5 pair weights we find from vanilla triplet loss, circle loss, binomial deviance loss, and the multisimilar loss. With the finding of the triplet weight and the pair weight, here we re-ensemble this weight together. In this table, it shows the mapping of different gradient combination of the triplet weight and the pair weight into existing demo losses. Also, we find under our Go framework, the combination labeled as the new are never being explored. Here is the VSE++ result on the different combination of the triplet weight and the pair weight. We find that the combination which has never been exploited achieved the best performance. Here is another test on the VSE infinity. We see the same pattern. Finally, we achieve a new SOTA record. And that's all. Thank you.